Welcome to Oddly Real. I'm Nem Stefanovic. Our everyday experiences suggest that all things have a definite position and a definite motion. For example, a basketball at rest on the ground has no momentum, and we know where it is. If we shoot the basketball along a trajectory into a hoop, there's a definite path that the basketball follows, with a momentum and position in every moment of time along the way. Yet, that's not how the subatomic quantum world behaves. There's a certain fuzziness to it. Nature conspires against us to know all of the properties of a particle, like its position and momentum, both at the same time and to a certain level of accuracy. There's an inherent trade-off where if you know more about one property, there is fundamentally more uncertainty about the other. It's not a question of improving the accuracy of the measurement tools or setting up a more clever experiment. There is no way to obtain the information. In fact, making an observation of a phenomenon will inherently influence the thing being measured, introducing uncertainty into its properties. However, there's an even deeper underlying behavior in the quantum realm. When we say there is uncertainty in the properties of a particle, like position and momentum, that implies that the information is there, that it's definitive, but we just don't know what it is. Strangely, reality at the subatomic level is not totally well defined, and particles don't have sharp edges in space. In fact, their very existence depends on an active observation, something that reveals some kind of detail of information, physical evidence, from the quantum realm up into the macro world. Until such an observation is made, the particle is in an odd state of indeterminism. How do we know that nature follows a strict rule of uncertainty? What do we mean that the state of a particle is indeterminate? And how is observation tied into this? Astonishingly, there are real experiments that demonstrate these behaviors, from which the laws of quantum mechanics have been formed. We begin with a simple experiment that demonstrates a phenomenon called diffraction. You can imagine a wave of something traveling through a medium and reaching a barrier with a single opening. For example, light travels as a wave, and this experiment can be devised to work with a beam of light with a specific wavelength to pass through a very narrow aperture. Part of the wave will continue through the opening, and it will spread out beyond the barrier. The spreading out beyond the aperture is what we call diffraction. We can conduct experiments with the wave by changing its wavelength, the distance between two adjacent peaks in the wave, or changing the length of the opening of the barrier. It turns out there's a relationship between the wavelength, lambda, and the opening length, let's call it L, such that the ratio lambda divided by L determines the amount of spreading of the diffracted wave. If the ratio is large, meaning that the wavelength is large relative to the size of the opening, then the slit is considered relatively narrow for the wave. This means the wave will spread out very widely beyond the aperture. However, if the ratio is small, meaning the opening is large relative to the wavelength of the wave, then the diffracted wave is narrow and doesn't spread widely. This simple experiment demonstrates a very deep principle of nature called the uncertainty principle. To understand this, it's important to note that particles on subatomic scales exhibit a strange behavior in that they can act as a particle or a wave in different situations. We call this wave-particle duality. For our purpose here, we'll just say that particles are able to travel as waves, but when they are measured, they take on particle-like form, with a definitive position in space. The wave tells us the probability of finding the particle somewhere in space, but ultimately, when we take a measurement, we'll determine specifically where the particle is. There's a randomness to where we find the particle, and this can be demonstrated by repeating an experiment over and over again. Light exhibits this behavior, since it can be demonstrated to travel like a wave, showing interference patterns, which are inherent to wave-like phenomena. However, light can also be detected as discrete particles, or photons, when measured with photon detectors. Even stranger though, it turns out that not just light exhibits wave-particle duality, but all matter as well. For this reason, the uncertainty principle is universal, applying to everything. In the diffraction experiment, we can think of the waves as probability waves for a particle. If the ratio of the wavelength to the width of the opening is large, the diffraction wave is spread out at the detector, meaning the particle has a probability to hit the screen over a wider area. In order for the particle to hit the detector over a wider range, it must be moving laterally with more momentum. Thus, the particle's position is restricted to pass through the narrow opening of length L, which results in a wider diffraction or more sideways momentum. If the ratio of the wavelength to the width of the opening is small, the particle hits the detector over a much narrower region. We know the particle goes through the opening, which has a length L. If the particle is detected over a more narrow region, it has less lateral momentum, since it doesn't deviate too far. Thus, if the particle goes through a wider opening of length L, it results in a narrower diffraction, having less sideways momentum. It turns out there's a relationship between the length of the opening L and the particle's momentum. This relationship captures the essence of a universal law called the uncertainty principle. And we can write it down as delta x times delta p is greater than or equal to Planck's constant, h, 6.6 times 10 to the power of minus 34 joule seconds, where delta x is the uncertainty in the position of a particle, and delta p is the uncertainty in the particle's momentum. In other words, between delta x and delta p, there must be some minimum level of uncertainty. We can't know both values to any degree of accuracy. It doesn't matter what equipment we use or how we set up the experiment. In every situation, there is always a trade-off between the uncertainty in a particle's position versus its momentum. It's a principle of nature itself. It's worth mentioning that there's another way to interpret this kind of result. Consider again the single slit experiment using light. In this case, we won't think about the problem from the perspective of a wave and diffraction. Instead, we'll think about particles of light, or photons, passing through the slit. However, in the quantum realm, light doesn't behave as we would expect. It doesn't travel in a straight line path. Particles of light, in actuality, travel in every kind of path. In fact, there isn't a specific preference for one particular path that light can take versus another. Some paths are very strange and counterintuitive, such as traveling in a curved path. Yet, the aggregation of these paths results in a common expected behavior for light at the macro level. The unusual curved paths have differing lengths and travel times, and they tend to vary a lot more between each other. Thus, these kinds of paths contribute less to the overall probability of travel and even cancel each other out. Other paths light can take have more similar travel times and paths, so they tend to contribute more to the total probability of the aggregate light path. When all combined, we see light take its familiar direct path through space. In the diffraction experiment, there is one single opening that photons can travel through. As per our description, the photons will take every possible path through the opening, including unusual curved paths. If the opening is large enough, these strange, more varied paths contribute less to the aggregate probability and cancel out as usual. Thus, light will appear to travel through the aperture, taking a very direct route and project a narrow beam of light. Alternatively, when the opening is reduced in size, only a very small portion of light will travel through the opening, so the output becomes dimmer. However, the paths that light can now take are all much more restricted, closer in length, and very less between each other than if the opening was larger. Thus, more of the unusual paths will contribute to the aggregate macro-level perception of the diffracted light. Thus, we see a wider, more distributed spreading of light beyond the aperture. Let's examine the famous two-slit experiment. In this case, light is shone through two openings in a barrier, and the light pattern is observed on a screen behind the barrier. We can set up the experiment such that when light passes through the openings, we see an interference pattern on the screen. The two diffracted waves interfere with each other prior to reaching the screen, resulting in regions where the waves are constructive, making bright lines, or regions where the waves are out of sync or destructive, canceling each other out to produce dark lines. This was one of the major reasons why light was thought to be a wave in the 19th century. However, modern experiments have been conducted where light can be demonstrated to be particle-like or made of photons. The light source can be made to be extremely dim. Furthermore, the photodetectors at the screen can also be connected to speakers to produce an audible noise when light is detected. In this case, since the light is so dim, individual click sounds are registered every once in a while. The clicks are always the same, producing consistently loud noise. As such, light is being delivered in discrete packets or chunks of energy. These are individual photons. In one experiment, we can cover one slit and monitor the resultant light pattern on the screen over time. When there is only one slit open, there is no interference pattern. There is just a smearing of light, much like our diffraction experiment. However, if we let both slits be open and we use our dim light to produce one photon at a time, something very strange occurs. Each photon passes through the slits and hits the screen at a random position. Repeat this process over and over again. In time, if we mark every photon position on the screen, the overall pattern will once again show interference. Our normal intuition would suggest that a photon traveling through the slits would have to pick one path, the left side or the right side, and travel through and hit the screen. Yet, this doesn't happen. To see that interference pattern, somehow the photon has to go through both slits at the same time. This experiment demonstrates a deep fact about nature and the underlying quantum world. The photon is not just a particle that passes through the slits. It doesn't take one path or another as it travels. The particle itself is in a kind of wave-like state, passing through both slits at the same time, until it is measured in one definitive location. This is so strange that it's reasonable to want to learn a little bit more about how a single photon can go through two slits at once. We can conduct another experiment. In this case, let's make an observation of the light at the point where it passes through one slit or the other to report back to us which path the light took prior to hitting the screen. Yet, when we do this, all of a sudden, the interference pattern vanishes. By making an observation earlier in the experiment, we've determined the position of the particle, and now it behaves more like a regular particle in motion without interference effects. Things get even stranger. Imagine if our experiment was conducted over an enormously large scale, like a two-slit experiment that takes light many minutes to travel from one end of the apparatus to the other. Imagine now a photon of light is sent towards the two slits, so the experiment has started. Yet in this case, we can delay our choice of how we measure the photon. For example, if we measure the photon using a screen past the two slits, we would get an interference pattern, so the particle acted wave-like. Alternatively, if we measure the light in a way to know which slit it passed through, we produce a particle-like photon behavior with no interference. Even delaying the experimental setup until the last split second, the particle will behave as defined by the experiment to be particle-like or wave-like. There is no definitive form that the particle takes within the apparatus prior to its observation. It is truly in an indeterminate state. Only the observation or the outcome of the experiment results in a record in our macroscopic physical world, which makes the phenomenon real. There is no phenomenon until it is observed. Finally, let's talk a little bit about what happens when we measure a particle and what qualifies as an observation. We said there is a certain amount of uncertainty that any particle has related to its position and its momentum. There is a trade-off with the uncertainty principle requiring a baseline minimal amount of uncertainty. What does this mean in the real world? Whenever a measurement is conducted on a particle, the act of measuring will influence the particle, thereby changing it in an unpredictable way. Additionally, we can't conduct two measurements on one particle at the same time. So we can't read both the position and momentum together. You set up one experiment to read one value, and in doing so, you get one answer. Additionally, there is no contradiction between the wave-like and particle-like nature of particles, since in either situation, you are conducting an experiment meant to test either a wave or a particle, not both. The experiments are considered mutually exclusive. We don't need to try to fit particle ideas in wave experiments and vice versa. The experiment itself will dictate the use of one model versus another. Regarding observations, this is what happens when something from the quantum realm or subatomic realm is revealed and amplified up into something tangible in the macro world, which is our world. For example, the clicks that happen from photodetectors upon incident photons relay information to us to hear. The visible pattern of interference on a screen is visible to the eye. Any kind of physical record in the macro world counts as an observation. I hope you enjoyed this episode, and remember, oddly real, really interesting.